So yeah, Python performance. Just a quick. How many of you think that Python is slow or not fast enough? Okay, good. I mean, I asked the same question at PyCon Italy, and like almost nobody raised their hand. So like, very different audience. So like, motivation of this talk. I've been doing Python performance for many years. For a long time, I've been a core developer of PyPy. So trying to make Python fast by rewriting it, rewriting the VM in Python, and like applying advanced techniques for JIT compilation and stuff. I noticed that talking to people at conference and stuff, I often get into conversation, and from my point of view, there are things which are like, let's say, obvious, and okay, like Python is hard to optimize because this, and that, but from the point of view of like a general Python programmer, sometimes it's not so obvious, not so clear, and there are kind of misconceptions. And so the idea is, let's try to put some, like streamline some of this thinking into a talk. So that's, I like to call it myth in the sense that, yeah, like, there are things that a lot of people seem to believe, and in my opinion, they are not true or not completely true. So let's try to have a kind of a sense of it. So the first myth which I would like to debunk is that like Python is not slow, but like their hand raising stuff before should have convinced you. Like many people actually tell me like Python is not slow because it's just a glue language, and or like in the modern version is that nowadays only GPU matters, and like so Python is fast enough, which is actually partly true, like in the sense that like you have kind of a set of program where Python is fast enough, and actually that's why Python is useful and used, and there are so many people here, because it's something that you can make real stuff with. But there is like, on top of it, there is a set of programs for which Python is not fast enough, and that's why we are spending so much time and effort to optimize it. And when I say we, like in general, like, there are people trying to make Python the language faster, an interpreter. There are people trying to make their code faster, and they spend a lot of time trying to optimize with Cython and Numba and other stuff. But ideally, in my dreams, I would like Python to be like even better than that. Like there is a lot of programs that just Python is not good for, because if you want to go very low level, or if you want to get this as much raw performance as you want, just Python, it's impossible to use them in that areas. And it would be nice if basically we make these circles larger and larger, and Python can fill more of this space. And like corollary of this is just a glue language is that like very often people say, oh, you just need to rewrite the hot part of your program in C or C++. That's actually what people said like 20 years ago or 15 years ago. Nowadays, they say that you should rewrite in Rust. And which is, I mean, again, like it's not completely false. Like it's actually a good technique to speed up things. But very soon you hit a wall. Like there is this thing called the Pareto principle. And I didn't feel like writing the slide, so I asked ChatGPT to do it for me. So basically, Pareto principle means that like 80% of the time is spent in 20% of your program, or some other like 90-10 or whatever, which means that there is a small part of the program which accounts for most of your runtime. So if you optimize it, then you get a good performance, which is true. But the problem is that if you do that, you quickly arrive at the problem in which, like, what was the hot part now is very fast, and then you need to optimize everything else, and then, well, you don't know what to do. And I think that's just a diagram which explains it. So at the beginning, I have an inner function, an inner loop, which occupies vast majority of my runtime, and then I optimize it by rewriting it in C++ or Rust or Numba or whatever, and then now it's very fast. But then, well, how do I optimize the rest of the programs? Maybe now I no longer have an inner loop, and that's actually what happened to me in practice. For many, many years, I worked as a freelance consultant to like go to people and try to make their code faster. And yes, you can do something, but then you hit a wall pretty quickly. And the other, like, I mean, it's kind of, again, corollary of the first. Like, you need to rewrite stuff in C and C++. Because what is not written in C++ is slow because it's interpreted. Like Python, like CPython is an interpreted language, and then yes, like if you are not an expert of VMs and implementation language, that's actually a good approximation. Interpreters are slower, but then like you can quickly become convinced by people going, announcing projects, say, okay, this new project which is coming will be fast because it uses LLVM or some other shiny technology. And nothing against LLVM, of course. But I think that things are much more complicated than that. Like, interpretation is just a small part of why Python is hard to optimize. And I would like to show it like a very simple example. If you are in a low-level language, like in C++, and you have this line of code, p.x times 2, and you are a compiler, and you can compile it to something very simple, which basically boils down to 3 CPU instructions. You load the value of x, you multiply, and you store it wherever it needs to be stored. But if you do the same in Python, this has nothing to do with interpreter or compile. This is the semantic of the language. You have this line, p.x times 2. What do you do? This is a very simplified version of what actually happens, but you need to find the type of fee. You need to find whether it is under get attribute or maybe it has been overridden, and then you call it. And then what is the type of p.x? Well, we will see. And then you need to call dundermul, or maybe it's rmul, or I don't know. And then you need to box and unbox everything because in Python all the objects are kept in as like references in memory, and then you unbox also the 2, then you multiply, and then you malloc something to contain the result, and that's what Python does. So this has nothing to do with the fact that it's interpreted. Like if you use Cython in pure Python mode, and you don't give that implementation, Cython needs basically to do this thing to give the semantics, and like that's slow. So fast forward, we arrive at a time in which now everybody uses static types. And like, very often people tell me, okay, but now that we have static typing, then I think it's easier because if I have this function which adds to integers, then if I'm a compiler, I can just use the type annotation to produce faster code, and everybody is happy. Not completely, because well, there are a lot of ways to just like convince the type checker that the program is correct, but actually is doing something different. And this is perfectly valid Python code. It works. It adds 2 strings instead of two integers, and the type checker is super happy because I tell him, yeah, trust me. And so if I'm a compiler, I just cannot believe in them. So they're completely useless from the point of view of optimization and performance. And it even becomes like worse than that, because this is also like code which is perfectly fine in Python. I can have a class with a custom dunderad, and then I can remove it later at some point. And then what do I do? Like if I assume that in this function I can call dunderad for doing x plus y, well, no. In that case, I should raise an error. So, like static compilation of Python is problematic because language, like everything can change. So I see Mark Shannon just in the front row. So Mark tells me, okay, you just write a JIT compiler, so we'll solve all our problems. Yes, I mean, I've been doing JIT compilers for a long time. JIT compilers can go a long way to make Python fast, or any dynamic language or interpreted language faster. But then we arrive at a more subtle problem. And I feel that you have this like trade-off triangle, and yeah, you can have dynamicity of the language, you can have speed, or you can have a simple implementation. You cannot have all the 3 of them. So for a long time, Python stayed in this, on this side of the, on this edge of the triangle. We had a dynamic language, and we have a simple implementation, which was slow. And now Python is going in this direction. We have a dynamic language which aims to be fast, but implementation is getting increasingly more complex. And you can say, okay, I don't care because I mean there are people in the front row doing it for me, and I don't need to care. But the problem in practice is that it becomes very, very hard to predict performance. And that's my experience doing it, I mean, with a different JIT compiler, which was PyPy. But like you arrive very often at the case in which you need to think what the JIT compiler will do and write your code in such a way that it triggers some optimization, but then like it becomes increasingly complex. And I found cases in which I was totally unable to trigger optimization in the PyPy compiler because the code was too complicated. And I knew very well how the compiler worked. So that's something to take into consideration. Like, yes, JIT compiler helps, but becomes very, very hard to get the top performance and the maximum, or get the maximum out of it. And we arrive at this problem, which I call optimization chasing, in which like you start with a slow language, let's call it Python, and then you optimize the fast path, and you say, yeah, I know that most of the time, yes, sure, you can delete methods from a class, but you never do it in practice. So I optimize, and as a JIT compiler, I assume that this thing doesn't happen, or that people don't mix types, or things like that. And then I get something which is either same speed as before, or faster, and everybody's happy. And that's basically what's happening now. But then I start to rely on these speedups. And I write code and put in production and get a number of requests per second, everybody's happy. But then eventually I risk to hit a problem. Like maybe this code is fast exactly because like the JIT compiler is able to hit all the fast paths and optimize a lot of the abstractions away and a lot of the slow path, but you never know. Like it happens that you make a line of code, you change a line of code somewhere, and then you have 2 times slow down. My favorite is at some point something in a program running on PyPy become like 10 times slower, and then it was Python 2 era at that point. And then it was because someone was mixing some line of code, was putting Unicode key in a dictionary of strings, and then well, you had to de-optimize everything, and everything became very, very slow, and then well, took 1 day to chase it. So like that's like very, very quick show of what I find problematic, and but I would like to go a bit deeper at trying to understand exactly why things are so complicated in Python. And let me drink something first. I like to start with this slide. This is completely random code. I mean, it doesn't do anything intelligent, but it's like 3 lines of code, and if as humans we read this, it's kind of obvious what it does. So we are importing NumPy, and then we have a constant which is 10, and then we have a function which takes well, an array and a constant and returns a float, and then I call some methods on it. Like if we do a code review on a pull request, well, that's what we expect. But if you are a Python compiler, then you cannot assume any of these things. To start with, NumPy could be something else, because it could have an import hook who completely changes everything, or I can put something in sys.modules which overrides. And so to start with, we don't know what we are importing. So we cannot assume anything. Then, of course, like the global constant, maybe it's not a constant. We will never know. And then type implementation, as I showed you earlier, they can lie. So like, from the point of view of the compiler, you need to assume the worst, but you don't write that code in practice. And sometimes you do. But like, there is kind of a delta between the way humans write Python and the way the language is defined, and this delta makes life complicated for the interpreter. And maybe we should like try to remove, because in practice a lot of stuff that Python allows don't happen. And yeah, basically this extreme dynamicity of Python is what makes Python slow, but at the same time is also what makes Python very nice, because I mean, a lot of these dynamic features that in 99% of the case you don't need, in the 1% is what you need to make Python awesome. A lot of libraries use patterns in which like you do meta-classes, decorators, change language, change classes, monkey patch, to create a nice API that end users can use nicely. So you cannot just remove them. That's a trade-off. And then I would like to play the compiler game. So now we imagine to be a Python compiler, and I show you pieces of code, and then we try to see like what we can assume about it, and how we can like generate code to run this code faster. So we start with a very simple class, which is a point, which has two attributes, x and y. And then I have a function which takes a point. I don't believe type annotation, so I put an assert. So this time I know that p is a point. And of course, I try to print the name, and the compiler should emit an error, because, well, we don't have this attribute. But of course, we can totally add attributes to objects outside the constructor, and this is supposed to work. So as a compiler, I cannot assume the shape of instances based on the type, based on the class, even if I know what is the class. And that means that any attribute access needs to, well, do a complex lookup. I cannot even assume that a method exists or doesn't exist. Like, this is not something that you find in production, I hope, but it's totally fine Python code. Like, half of the time this code works, and half of the time it raises an exception. Good luck compiling it. And it's part of language semantics. And we can go further. So we have a class student, which has a name and has a method to, well, do studying and learning stuff. And then I have a class, a student who goes in Berlin. Actually, note that this class is not even a subclass. It's completely unrelated. But it happens to have a method study. And then I create a student, Bob. And then, well, I mean, here, when I need to call p.study, well, I just created this object. And like, there is no way that go to Berlin can like modify the binding. So this p must be this object which I created. And so if I'm a compiler, I can assume that it is a student, like, right? Well, it turns out that this is totally fine Python. This works. And I actually wrote code to use this thing at some point in my life. And if you are an interpreter or a compiler, you need to take it into account. So you see, like, the kind of Python that people actually use in practice and the kind of Python that it's allowed by the language. Let's try to make it better. So we have a class person, and then we have a class student, which is, again, unrelated. And then I create a person, Alice. And then, well, I print name and age. This works. And then, OK, now, it will be a person, right? Like, I don't do anything else. I don't go to Berlin. I don't do anything like. No, because this is, again, totally fine Python. You can have a class with it under new, which returns something which is unrelated, and it's not instance of the class. And, well, good luck at optimizing that. So here we have a decorator. So we have global variable n, and we have a decorator which returns n. So we have a function which returns n, and we have this magic decorator. And then, like, let's desugar it. Decorator just means that it's a function which takes foo and returns something else. So we can, I rewrite it as like bar equal magic of foo, and then, yeah, like, Of course, like, I could just return a different function, but no, like, in this case, if I'm a compiler and I can double check that, yes, the code object of the return function is still exactly the same as before, so I didn't change the code inside. It's still in the same module, and no, it's not importing a module from somewhere else. And it's not a closure. But yet, if I call foo returns 10, if I call bar returns 20, how is it possible? Like, the n is still the same, and this code like, really passes. And it turns out that you can write something like that. You can take a function and create a complete clone of the function with just get different globals. So the n, the return n, doesn't look up the actual global of the module, but returns up like a dictionary that you pass to it. Again, good luck optimizing that. And you could start thinking, okay, yeah, you're making things which are more and more like very, very complicated. Nobody uses it in practice. It turns out that this code exists in real world. There is this function which is part of PDB++, and you could say, okay, yeah, go to that guy and tell him that he's crazy. If not, that this guy is me, that I wrote this code years ago. And I claim I had good reason to do that. So this is kind of like the crazy part of it all. Yeah, there are features which you need to take into account. But the other problem, and this is like more fundamental, is that in Python, abstractions are not free. Like, when you write code, you want performance, but you also want the code to be nice, maintainable, and easy to read, easy to write. And usually you do that by creating abstractions. And like we start, from example, from an algorithm. It takes a list of points, and the points represent as a tuple of two floats, and then we do something on it to compute. But then we would like to, I don't know, to factor out this because we don't like to write it in line, and we create a function. But then this code is already slower than before because, well, you need to call this function, and then you need to create a frame object, and you need to do lookup. Again, a JIT compiler can help, but like it's not fully, by the way, and well, it creates a bit of overhead anyway. But then, like, okay, points as tuples, we don't like them, we put it in a data class. This is again slower than before, because instead of accessing like items of the tuple, we need to have an attribute access every time. And I showed you earlier, attribute access is slow. And so like every time, like, and this is like a contrived example, but in real code it happens. Like you want to build abstractions, and every abstraction has a cost. And then you end up with a program which is very slow. And this is, I call it this Python to Python abstraction. Like I'm refactoring things in Python, and I'm making them slower. But I have this thing which is like Python to C cost. And this is something which is more or less more potential than actually true, but it will be more and more true the more advanced the Python interpreter and JIT compiler becomes. Because you can totally imagine to have a special implementation for a list of points in which you want to have a list of like individual integers or floating points which are not boxed, so you don't have to allocate stuff. And then the interpreter is able to use this fast implementation to avoid a lot of the cost that I showed before. But then someone arrives, and I know I go to the first slide and I rewrite part in C, so it's faster, and I write this speed up module for speed. And when I pass this P, which is the point, to the function, then if the interpreter was able to use this special representation in which the point is actually not allocated, well, I need to allocate it at this precise time just to pass to the function, which then takes the two integers back, and this is completely unavoidable with the current C API, it's just completely useless work because we just need to create this costly and complex implementation just to pass that around. And this is, again, it's a problem which is basically unavoidable with the current technology stack that we have, and it's a problem which was very, very present in PyPy, and a very good way of speeding up PyPy code was to delete the speedups written in C and just to write the pure Python code, and then the interpreter was able to optimize across. And this, again, it's a problem that I don't know how to solve. And the elephant in the room is that, I mean, there is another problem that I rarely hear, actually, and it's memory management. Because Python is, the way Python behaves is inherently problematic. In modern hardware, well, basically, with modern CPUs, we can say that computation is very cheap. Like, you can do numeric computation very, very quickly, but memory is the bottleneck very often. And so if you have your data already in cache, which can be multiple levels, it's very, very fast. But if you have your data in general memory, getting to the memory is very, very slow. And generally speaking, if you want to have very, very good performance, you should avoid cache misses as much as possible. Cache misses is when you try to load an address and the address is not in the cache, so you need to get back to the RAM to wait for it to arrive. And I created this, when I say horribly slow, I mean this. The speed of getting something in L1 versus the speed of waiting for RAM access to happen. So if you have a program which is cache unfriendly, well, basically your CPU is always waiting for memory to load. And but that's the way Python behaves. It makes it very, very prone to have this kind of layout. Like, imagine again our person, which is an instance with two fields, name and age, and then I have a list of them. And ideally, for cache friendliness, I would like all this thing to be in memory altogether, so that if I iterating over the person, then, well, okay, the time I need to load the next person, well, it's already in cache because the CPU knew that it's next to it. But in practice, this is what happens. Like, this is a visualization of memory layout made with PyTutor, and you can write the code which I showed here, press play, and then it shows you the actual graph in memory. So we have the frame object, and basically every arrow means potential cache miss. It's a pointer chasing, and which means that things are around in memory, and potentially this is a cache miss, which means that there's very slow red dot which I showed before. So we have a frame which has a list of 2 items, and the first item is a person, and then the person has a name, which is a string, and then actually there is another arrow, which is the buffer probably, and then we go back, and then we go to the age and stuff. So this is something that you cannot just solve with the JIT compiler. It's impossible to solve it without changing semantics. So Python, I claim it's inherently cache unfriendly, and I honestly don't know how to solve this problem. Maybe other people do. So conclusion somehow is that the sad truth is that Python cannot be fast. Maybe you hope that you arrive here and then I show you, let's make it very fast. No, my conclusion is that Python cannot be super fast, can be fast enough, but not the kind of performance that I aimed for, without breaking compatibility. So if we want to keep all the, let's call it craziness, we understand what I mean. It's nice things, but also a bit crazy. So if we want to keep this craziness, well, we have to leave some performance on the table, and it could be fine. So they said this the end somehow. And so I did this talk at PyCon Italy 1 year ago, and I concluded, yeah, that's the end. But I would like to give a bit of hope. And so basically, I think that we should underline this without breaking compatibility part. And my proposal for the community is that how we can move forward. Well, if we want to reach, and it's a big if we want to reach that level of performance which I am for, and it's fine to say no, then we need to tweak language semantics. And I claim that we should keep dynamicity where it's actually useful, for example, to do like meta classes, decorators, and stuff, but at a very precise point in time, and not to allow the word to change at any point in time as it is now. We should redesign a type system in a way that which is actually useful for performance, because the current one is like stick on top of the semantic and cannot, like because of design, cannot be useful. And ideally, we would like to be able to go to low level, like don't have to rewrite things in C, C++, or Rust. Right? Should be able to arrive at that level of performance while staying in this language. And at the same time, like I should be able to go to C without paying the cost of C abstractions. But most importantly, we want something which stay Pythonic, because we like this language, else we wouldn't be here. So like the conclusion is that, yeah, I actually have a potential solution for this, which is not to make Python faster, because I claim it's not. So let's call it differently. I started a couple of years ago this new project, which is SPY, which stands for Static Python, and it's all the standard disclaimers, like it's WIP, work in progress, research and development. We don't know where it will go. If you are interested in it, the best source is, well, GitHub, of course, but this link to the talk which I gave 1 month ago, 2 months ago at PyCon Italy, in which I go and explain the details of how it works. I would like to show a demo of it. I don't have a lot of time, but just to give you an idea of where we are going. You can also try on your mobile. And now I need to, because I see different things on my screen and on the projector. So let's see if I can, yeah. So this, and then, yes. So this is the demo. So this is based on PyScript, so it's by Python in the browser, the other project which I was doing at Anaconda until some time ago. And it's image processing done with Python. So I'm getting frames from the camera, and then it's doing edge detection, and you can see this is like pure Python using NumPy, and I try to make it as fast as possible by using NumPy, and that's what I managed, whooping 0 to 2 FPS. And if we, it's not the same code, but the same concept written in SPY. I click on this, it takes a while just to get the event, but this is like the performance of SPY. And it goes like 60 FPS, but I think it's actually bounded by the FPS of the camera itself. Like on my Mac, it goes to 120. And that's the kind of performance that I aim for. Like you should be able to get this by writing things in SPY and not by writing, like having to switch language. And yeah, that's the conclusion. And oh yeah, like before I forget, like if you want to follow more development of SPY, like the GitHub, of course, contributions are welcome. I have also some issues which are labeled as like a good first issue, help wanted. So if you are interested in compilers and interpreters, that's actually a nice way to get it. And as part of the OKRs for my employer, Anaconda, I had to say, okay, let's try to make community more involved, so let's create a Discord server. So I created a Discord server, and if you want, but you are not seeing what I'm seeing, that's why. Oops. Yeah. So you can join the Discord server, and let's see if we can make this number higher than 3 members that is now. Okay, I think I'm done. I mean, and yeah, I think it's time for a question.
1, 2, 3. Thank you, Antonio, for your great talk. And participants, I would kindly ask you to proceed with the microphones if you have any questions to Antonio.
Yeah. Hi, great talk. Thank you very much. I have 2 questions. So on the slide that you show that we can't make Python faster without breaking back compatibility, right? Aren't you implying that we should like go from Python 3 to Python 4? So that's the one question. And just the second one. On the next slide, where you're showing the possible solutions, so aren't you afraid that with all these stacking layers, so we have different coding principles for like dynamic Python, different for performant Python, and we stack this into the free threading Python, we're suddenly in totally separate language than Python is right now. Aren't you afraid of that?
Okay, let me answer the first question. So, if I understand correctly, your question is, so since I claim that we should change the language, let's call it Python 4. So the Python, as like Python community know, Python 2 to 3 transition was like painful and semi-state that we should try to avoid again. And the problem of that is that it was impossible to do incremental migration. So Python moved from Python 2.7 to Python 3. And you had to choose either everything in Python 2 or everything in Python 3, and that's why problems began. What I'm trying to do with Spy is something which can integrate with existing Python. So, like, there is a modality in which you write code in Spy and then you generate a CPython extension. Currently, like, it's very, very limited, but like that's what happened in my demo actually, and. But you don't need to migrate all your code to Spy, so you can do it incremental, and I think it's much, much better way. I'm not in position to call anything like Python 4. I don't think there will ever be a Python 4, but like the number is not important, I will say. And the second question, what was it again?
When we go for...
Would we have the different language and something? Yeah.
I don't understand the different language. Like,
if we introduce different types of the performant Python.
Yeah, so maybe so when you're showing all those possible solutions, which are great, and we're adding all those changes we have in Python right now. Suddenly we are getting to another place than Python is. So Python will be different than it is right now, and we like the Python right now, right? So.
Yeah, like, sure. That's the important part of staying Pythonic, where I say, like, ideally, I would like something which is still as nice as it is now, but without the drawbacks. Yeah, I mean, we cannot change things without changing anything, yes? So there is the risk of making something worse. We will see. That's the best answer I can give.
Thank you. And I also have one question for me. So do you have some simple and straightforward recipe on how to find the good balance between the performance and the readability, maintainability of the code, so that you probably follow in your projects?
No. The sad answer is no. My experience is that like Python tends to make to create cost whenever you try to abstract, is what I showed before. And the best thing that you can do is, like, yes, identify the pieces of code which are performance.
The bottlenecks.
The bottlenecks, yes, and try to put the bad stuff just in that. But it is not scalable approach, and but again, it depends what we mean by bad performance. Like, Python is totally useful and usable for many things. If you have something which is I/O bound, you don't care about CPU performance, CPU bound performance, so that's fine. But when you start caring, well, a lot of people are just writing stuff in Rust. There must be a reason why.
Yeah. Okay. So thanks once again, Antonio, for your talk, and let's once again.
I'm sorry. Can I ask a question?
Yeah. Sorry.
Yeah, I'm sorry. So I just want to ask about this thing, because in theory it's really nice, and I agree, and I was wondering from the start of the presentation just about that. But the thing is, where do you make the cut? Because, you know, people want easy solutions and that never works. And for example, with free-threaded Python right now, it's just a thing that is very connected to this because you're trying to get the performance in cost that you are losing something. And that's the guild, right, that was there to protect people. So where would you make the cut? Because, you know, I think it's like user responsibility to realize that you are not going to get everything.
It's impossible to answer this question like without going into details, basically. So you are basically asking. Okay, I don't understand what you are asking.
I know it's difficult, but I'm very surprised with this direction with removing GIL in a way because it's against some ideology. So I wanted to like, where would you like make a distinction where staying Pythoning and like not leaving these things, and you know, because if you say okay, so we'll do it like in a good way.
So I claim it's impossible to have like to solve all the problems without change. Again, we cannot change things without changing anything. And so free threading is a completely different like topic, I would say, and it's not really relevant to what I said. I also personally don't think that free threading is the solution to like having concurrent Python on the CPU, but that's like just my take, and I'm not an expert in the field. So for SPI, what's happening is that it's really like an opt-in thing. Like I also have a different extension. You don't write .py file, you write .spy file. So you need to like opt in and choose. And choose these new features, and it's perfectly fine to say I don't need them, but I'm not sure I'm answering your question, but I'm happy to talk about it later.
Okay, great. So in case of questions remaining, I think you can find Antonio around. So, and let's once again thank Antonio for his great presentation.